building a model in Heli-Dyn is pretty straightforward. In fact, when you first open the Heli-Dyn screen, what you see is the main tab. It's the Model Inputs tab. And underneath this tab, you have sub-tabs which are called Component Models, Center of Gravity and Inertia, Main Rotor, Tail Rotor, Fuselage, Wing, Horizontal Tail, etc. What you need to model is simply geometric properties of the helicopter, inertial properties, and some properties of the dynamic components that you will use to model your helicopter. So it's using a component build-up system. So where we are modeling the main rotor, tail rotor, fuselage, wing, horizontal tail, vertical tail, landing gear, one by one, and those components are added up at the end at the center of gravity in terms of forces and moments. So for instance, if I want to model a certain main rotor, I have a few options to choose from. Through this pull-down menu, I can choose between a blade element momentum theory model and a blade element model that uses a Peter-Shaw finite state dynamic wake model. So let's choose the more advanced one. And once I use this model, I can go to the sub-tab called Main Rotor, and the appropriate values that I need to build this particular component appear here on this tab. So what I need to now input are the numbers for these values. For instance, I need the station line, water line, and a butt line of the main rotor. I also need the radius. I also need the blade chord. If I have a blade twist, I can input a blade twist. If I don't have a blade twist, I just put 0. I can set the number of blades, then the RPM. If I have a ground effect coefficient, if I want to include ground effect, we have something called a ground effect coefficient, and the definition for these things are all well explained in this button called Help. And there you will see a PDF a manual that will explain you what these numbers actually mean and how it is used in the model. We also have a theory model with Heli-Dyn Plus, which also explains these numbers here. So you might have a precone, you might have a flap. You definitely need a blade flap inertia. You might have a hinge offset. So if you have a bearingless or a hingeless rotor system, you might think of an effective hinge offset you might want to put in here. And this is in terms of percentage of the full rotor. Once again, you can go back and check in the help manual to see what each of these parameters actually mean. The blade profile drag coefficient belongs obviously to the main rotor. You have the lift curve slope, and this is all we input here. If you have it's a linear CL alpha graph, and this is where you put in the blade lift curve slope. You might have a shaft tilt both in Y and X directions, a delta 3 angle for the coupling of the pitch and flap, and if you have a stabilizing bar that also gives feedback to the system to increase the damping that comes through the main rotor. So, and what each of these parameters mean, as I said, you can go back to the help manual and check. So this is the main rotor. Coming back to components model, you can also choose models for the tail rotor. In this case, we have a simple blade element momentum theory tail rotor. So you go to the tail rotor tab and you fill in these numbers similar to what you have done to the main rotor. Then you do the same thing for the fuselage. The fuselage is simply modeled in terms of the equivalent flat plate drag areas. And you, of course, also have to put in the station line, water line, butt line of the point where these aerodynamic forces are actually acting. You might include a wing, or you might simply choose none, then you don't have a wing. Similarly with the horizontal tail. The horizontal tail has really three options. Either you don't have one, or you can have a 1D quadratic lift aerodynamic coefficient, or a 2D aerodynamic lift drag moment parameters. So one has only lift, but the other one has lift, drag, and moments that will act onto the system. Similarly, for the vertical tail, for the landing gear, you might have one. The landing gear modeling is done such that if you choose landing gear, it's an interesting one. You can go to landing gear, and once you choose landing gear, the landing gear is modeled as a bunch of spring damper systems. So if you have, let's say, a helicopter with 3 points of contact, for example, let's say you have 3 wheels, right? The way we model is then here you go to this tab and you choose 3, okay, and for the first landing gear or the first point of contact, you can put the position, you can point the position of this landing gear, so it will be a station line, butt line, and water line again for that landing gear. And then you put the spring and damping constants that are required to model the spring damper at that point. And then both in the X and Y direction on the point of contact, you have a friction coefficient. So static and the dynamic friction in both X and Y directions. So for one landing gear or one point of contact, you can have a spring damper system, right? With friction coefficients left and right. So if you have 3 of them, 1, 2, and 3, you basically define 3 points of contact, both with spring dampers, all of them with spring dampers, and friction coefficients. Now you can of course have 4, and this is typically what we use if you have a skid type of landing gear, right? Then we have 2 at the front and 2 at the back, and this gives you a pretty good model response on the ground. Another thing we included in the component model is a stabilizing bar, right? You can include a stabilizing bar, and I've just mentioned this in the main rotor tab. The ground effect, we have the Cheeseman-Bennett graph that's pretty well documented, and it's really a simple coefficient that adjusts for the ground effect as a function of the rotor radius. So this is something you might want to check later. Another thing we included is a simple stability augmentation system. So if you include a SAS to the system, you just go to the SAS tab and you have simple feedbacks. You have a feedback for phi, theta, and psi, the Euler angles, or for P, Q, and R, the angular rates. Or you might also have, if you want a feedback in phi dot, theta dot, and psi dot, the Euler rates, you can also have a simple feedback. A lot of helicopters use simple feedback, especially PQR feedbacks, to have to increase damping in some of the channels. And we found this pretty handy to adjust some of these damping values, both to include a stability augmentation system, but also from a modeling point of view. Sometimes some of the models might not model enough of the damping, for instance, and this is where you can make little adjustments. So finally we have a little tab for environmental conditions. Here I can adjust the gravity in case you might want to run this on another planet or something, and you can adjust the air density, and you can adjust the temperature. So this is the air density at sea level. So if I adjust the temperature here, it will automatically adjust the density in the model according to that particular temperature. So this is how you build a model. Once you built the model, you simply say save, and you will immediately have a place here to save, and you say my model. Let's say give it a name, and when you say save, this will be the model you have just built. So if you come back and you want to reload your model, you say load. Here's your model, and you can reload your model. Let's reload the default model, and you say open, and that's your default model, and immediately you will have the numbers you have just selected for your system. Now we found this button, it's called default, pretty useful in the sense that sometimes you would like to see what the default value for some of these parameters are, in case we are confused about some of these parameters. The default number, if I press default, it will basically open up the default model that comes with Heli-Dyn Plus. And in this case, Heli-Dyn Plus comes with a helicopter model that is similar to the UH-1H helicopter. So we found this button pretty useful when we model something brand new, and for new users, it turned out to be a pretty useful button. So this is how you model. So now we have a model, it's ready to use, and you can immediately go to the other tabs to do a performance analysis, trim the vehicle, linearize it, initialize, or run a few simulations, or even extract it and use this model now in MATLAB and simulate. So note that you have a full nonlinear model, okay, with pretty sophisticated inflow models and main rotor models with flapping dynamics and everything. And all this theory is well explained in the theory manual, which you might want to go back and check out later to see what these libraries actually have behind them. When you just look at Heli-Dyn, you might want to think that some of these models with just a few numbers are simple models, but these are pretty sophisticated nonlinear models. And and they're very simple to build. Once you build them, you can do a lot of things to analyze and run simulations.